Hello everybody. This is a lecture on sections 1.8 and 1.9. So these sections are on linear transformations. So a linear transformation T, and then we put a colon from R to RC. It is a rule for which each vector x in R is assigned a vector t of x in RC. Okay, and the rule satisfies the following two properties. Okay, property 1 is that t of the vector x plus y is equal to t of x plus t of y. And so whenever you add vectors and then you hit it by t, then that's the same as hitting x and y by t and then adding them afterwards. So this is adding vectors in the domain, r to the r, and this is adding vectors in the range, r to the c. It doesn't matter where you do it. And then the other property is that t of k x is equal to k times t of x. So we have those two operations for vectors, addition and scalar multiplication. Essentially, addition can be done in the domain or in the range. Scalar multiplication can be done in the domain and in the range or in the range without affecting the outcome. Okay. So by the way, if t from RR to RC is a linear transformation, and let's see, x1v1 plus x2v2 plus xmvm is a linear combination of vectors in the domain r to the r, then essentially what Rule 1 and Rule 2 are guaranteeing is that if you take the linear combination here and you apply C to it, or T to it, then this is going to be equal to, well, it's going to be the sum, like this, by property 1. You can apply property 1 and break up the sum inside of T to be a sum outside of T, and that's what I did here. Whether or not it's 2 terms, 3 terms, 4 terms, 5 terms, or more, you can break up 2 terms, you can break up more, because, a sum of more than 2 terms is 1 term plus the rest. And then the rest is the sum of the second term plus the rest again. So you just keep applying that addition property, and then you can always factor the scalars out. x1t v1 plus x2t v2 plus xmt vm. So if you take a linear combination of vectors in the domain and apply t to it, then that equals the corresponding linear combination in the range. Right, so addition and scalar multiplication can be done either in the domain or the range, essentially meaning that linear combinations taken in the domain could also be taken in the range instead. Okay? It doesn't matter where you do it. You always get the same outcome. Okay. So example of linear transformations. So in actuality, this is all linear transformations, but it takes some explanation to do this. So in a moment, we will see that all linear transformations t from R to RC to R. Oh, is that writing it backwards? These should all be RC to RR. RC to RR. And RC this is RR. RC to RR. RC. So the domain is RC. The range is RR. And, okay. Yes, RC to RR. All right. So in a moment, we will see that all linear transformations T from RC to RR have the following form. Okay, let A be an R by C matrix. In other words, A has R rows and C columns. Okay, define T sub A from RC to R number of rows. So this is presented R rows, C columns, but the linear transformation is the other way around. Domain is RC, range is RR. Define the transformation sub A from RC to RR by transformation sub A of vector x is just equal to A times x. This is a linear transformation. Because, as we discussed before, ax plus y is ax plus ay, and ak times y is equal to ka times y. So we discussed this in the previous section, so those are basic properties that make it a linear transformation, and we'll see in a moment that actually all linear transformations have a matrix of this sort. Okay, so there it is. For example, consider the matrix A equal to 1 minus 2, 1. So 3 minus 4, 5. 0, 1, 1. And minus 3, 5, 4. So this defines a linear transformation, right, from R to the number of columns, okay, 3 to R4. Okay. Another example, if we were to do the other way around, so this is 4 by 3. Come on. If we had this matrix here, let's say 1, 3, 0, and -2, -4, 1, 5, and 1, 5, 1, -4. This matrix defines a linear transformation from R4 to R3. Now, let me ask you a question. Does AX equal to B have a solution for all B in R3? Okay, so for any vector that I pick in R3, is there a vector in R4? Right, for every B in R3, is there X in R4 such that A times X equals B? Well, let's check it out. I mean, we've just solved this kind of thing before. You take this matrix, and if you want, you can put the unknown elements here, A, B, C. So B, A, little b, little c, like that. You can put these things here and then put it down to row echelon form and see if you ever get a row that looks like this. If you get a row that's all zeros, plus some expression over here, which may or may not be 0, then you don't always have a solution. For some ABC, you do have a solution, but not always. We did this problem before in previous section. Now, you don't actually have to keep track of these, but let's do it now just for kicks, and I'll cross them all out at the end. All right. So let's add row 1 to row 2, subtract it from row 3. So that's 0 minus 4 plus 6 is 2, 1 plus 0 is 1, 5 minus 6 is minus 1, and this is b plus 2a. Last row, 1 minus 1 is 0, 5 minus 3 is 2, 1 minus 0 is 1, minus 4 plus 3 is minus 1. And then this is a plus c. Right, and then I'm going to subtract row 2 from row 3, and I get 1, 3, 0, minus 3a, 0, 2, 1, minus 1, b plus 2a, and 0, 0, 0, 0, right? I'm subtracting row 2 from row 3. So I got a plus c minus b plus 2a, so that's a minus 2a, so that's minus a minus b plus c, right? A minus 2a, 0 minus b, and c minus 0. Now, you don't have to keep track of this. Okay, what matters is that you've got this row of zeros here. Right, you got this row of zeros here, and this thing at the bottom here may or may not be 0. So, again, as we talked about in the previous section, I forget exactly which one it was, and you've got pivots here and here, right? Your pivots are this row and this row with those columns. All right, so this system has a solution if and only if minus a minus b plus c is not equal to 0. So it does not have a solution for all b in R3. Just for some. Just the ones that satisfy this. Okay? Side note. Now, for this system with 3 rows and however many columns, so 3 rows and however many columns, to have a solution for all b in R, we need a pivot in each row. If we had a pivot in each row, like, if you had a 3 here or something like that, you don't. But if you had a 3 here, then you always have a solution. Whatever a, b, and c are, and whatever they equal to here, this means 3x3, right? This last row would mean 3x3 is equal to whatever that is, minus a minus b plus c. So x3 is equal to minus a minus b plus c over 3, which could be 0 or it could be anything else. You do have a solution if you had a pivot in each row, but you don't. All right? All right, a pivot in each row for that to always have a solution. We'll talk more about that a little later. Put some more sort of nomenclature on it. It's the same concept we talked about a while ago. But again, we're going to put some more nomenclature to it because in linear algebra, you're always looking at the material from different points of view. Okay, so it's important to have this nomenclature and have these different points of view on the same sorts of properties because they always come up in different ways. All right, so here's a theorem, is that every linear transformation from RC to RR, every linear transformation T from RC to RR is given by an R by C, given by a unique R by C matrix A. Okay, as a matter of fact, the columns of A, in particular, the columns of A are T of the vector 1, 0, 0, 0, T of the vector 0, 1, 0, 0, 0, T of 0, 0, 1, you get that idea, right? 0, 0, 1, 0, so on and so forth, like that. Okay, give that a quick proof. I'll be back in just a moment. Okay, is that going? Yeah. All right, so every linear transformation is given by a unique R by C matrix. All right, so So let's let C be C be equal to 4 and R be equal to 3. For any other R and C, it looks the same. Okay, so the domain is R4, the range is R3. All right, for any other version of this, it looks the same. All right, so now T of a vector in the domain. So which vector in the domain shall we look at? Well, let's just call it, A, B, C, D. All right, but A, B, C, D is equal to A times the vector 1, 0, 0, 0, plus B times the vector 0, 1, 0, 0, plus C times the vector 0, 0, 1, 0, plus D times the vector 0, 0, 0, 1. Like that. Right? This vector is just this linear combination. Right? And because T is a linear transformation, right, the linear combination in the domain can be considered as a linear combination in the range, right? 1, 0, 0, 0 plus B times T of 0, 1, 0, 0 plus C times T of 0, 0, 1, 0 plus D times T of 0, 0, 0, 1. So I'm putting both parentheses there. I probably should have did it here too. All right. Okay, is equal to, well, what is this? I mean, we don't know what it is, right? But let's just say that it is, so it's a vector in R3. So we'll just call it A11, right? A21, A31. I mean, it's just some vector in R3. And then T0100 is also some vector in R3. Right? It's A12, A22, A32. And this is also some vector in R3. So what should we call it? Well, we'll just call it A13, A23, A33. And this one, we'll just call it A14, A24, A34. Right? I mean, I don't know what those numbers are, but they're numbers. But what is this? This is just equal to the matrix A11, A21, A22. Right. A12. Well, I mean, I have to. Let me not do that. A22, A32, A13, A23, A33, A14, A24, A34 times the vector A, B, C, D. Right? How does this multiplication go? You take row 1, you take row 1, you multiply by the column. So it's A times A11, B times A12, C times A13, D times A14. And that's what you get right there when you add that together. That's exactly how we define the multiplication of a matrix by a vector. Right? Pretty clever. Pretty clever. So that's the end of the proof. So every linear transformation is, in fact, a matrix transformation. Okay? Here's your matrix A. That defines T. All right, and what is that matrix? Well, it's not a mysterious object. It is just T of these vectors, the elementary vectors. T of the first elementary vector, T of the second elementary vector, T of the third, so on and so forth. That's just the columns of the matrix. So as long as you know what those elementary vectors are, you're good to go. All right? Okay. Next. So let's take an example. Okay. Consider the following matrix. A equal to, and we'll say this is cosine theta minus sine theta, and then sine theta cosine theta, like that. What is the action of A as a linear transformation from R2 to R2? Well, let's look at what it does to the basis vectors and then just sort of extrapolate that to the rest. Okay, so here's R2. Here's the one basis or elementary vector, 1, 0. Right, so that's the vector 1, 0. And 1, 0 when you multiply it by the matrix, gives you the first column, cosine theta, sine theta. What is cosine theta, sine theta? Well, it's the vector right here. This is the circle of radius 1. Right, so that's the vector 0, 1, right there. Zero, 1. So this is if this is angle theta right here, this is A times 1, 0. All right, A times 1, 0 is equal to cosine theta, sine theta. That is the definition of, which is the first column here, that is the definition of cosine and sine. It's the x and y coordinate of the radius of the unit circle with angle of rotation theta. And then A of 0, 1, right, is the second column here, minus sine theta, cosine theta. Minus sine theta, cosine theta. So if you take this vector here and you rotate it the same angle theta, that's the vector right there. 0, 1. And this right here is the vector A, 0, 1, minus sine theta for the x coordinate, cosine theta for the y coordinate. So you gotta think a little bit about what the definitions of sine and cosine are, how it switches the x and y coordinates and such. Okay, so it's just a rotation. So the action of A on the basis vectors is just rotation. And therefore, in any other vector, which is a linear combination of these elementary basis vectors, you get the same kind of rotation. So matrix A rotates any vector in X in R2 theta, an angle of theta, in the clockwise direction, or counterclockwise direction. So these kind of linear trees, there's also a way of doing rotations in 3 dimensions as well. There's a 3-dimensional rotation matrix. So that's a 2-dimensional rotation matrix. There are 3-dimensional rotation matrices as well, and they use 2 different angles, theta and phi. You'll learn about how you do rotations like that in Calc 3 if you do take that course. You'll learn about spherical coordinates, and it'll talk about that kind of matrix. It's a long discussion, so I'm not going to get into it. But these kinds of matrices are really nice if you're working with computer graphics. Like if you're trying to encode vector-type graphics and figure out ways to move those vector graphics around. Well, rotation matrices are definitely part of what you need to do to move vector arrangements around and show them rotating. So these matrices are kind of cool. Rotation matrices. There's also reflection matrices and translation matrices, although not all are linear transformations. Okay. Final topic, definitions. Okay, a linear transformation. So now they're all matrix transformations, right? Or the linear transformation from RC to RR given by matrix A is said to be onto an onto linear transformation. Okay, when for every B in RR, when for every B in RR, there is X, there is a solution, X in RC, such that, well, to the equation, AX equals to B. So whatever vector you pick in the range, there's something in the domain such that when I apply A to it, I get to the guy in the range. Right? So everything in the range gets hit by something in the domain. There's always a solution to such a thing. Right? And what were we saying before? Right? So an R by C matrix A, okay, yields an onto, or defines an onto linear transformation from RC to RR if and only if A has a pivot in every, well, let's if and only if, let's do it this way. Right, AX equal to B has a solution for all B in RR if and only if, right, A has a pivot position in every row. So this onto property is simply determined by the matrix A having a pivot position in every row. Okay, that's all. Okay, but we need to understand what it means in terms of linear transformation. So this is all just terminology and words here. I mean, I haven't done any math here, no calculations. It's all just terminology and words, building upon stuff we've already talked about. Right? That this equation always has a solution when there's a pivot position in every row. And in terms of linear transformations, it means linear transformation is onto. Right? So it's just a third way of looking at this thing. So what about, so that's when A has a pivot position in every row. What about when A has a pivot position in every column? What should that mean? That should mean something else. Well, it has a pivot position in every column if the columns are linearly independent, right? And in terms of linear transformations, it has a really nice property that we can discuss. So you will see. So let me say it in the exact same way I said it here. Where's my cursor? The linear transformation from RC to RR given by matrix A is said to be, the term is 1 to 1, if for every B in RR there is at most one solution to AX equal to B. That is, AX equal to B has a unique solution or is inconsistent. So not multiple solutions. Not multiple solutions. Right? Just one solution. Okay? Well, you know, we talked about this before, right? A matrix has the solutions we have discussed before in section 1.5 that the solutions to AX equal to B are of the form X equal to, so we'll call it P plus N, where P is a fixed solution to AX equal to B, that is, well, where AP is equal to B. So it is a fixed vector with AP equal to B, and N is any solution to AX equal to 0. So now we're talking about linear independence, linear dependence. Linear independence and linear dependence. This guy always has a solution, right? X equal to 0 is always a solution. It's never inconsistent. So either you only get X equal to 0, the trivial solution, remember? It's called the trivial solution. Either you just get the trivial solution, just this one, or you have a free variable and there's infinitely many solutions. That's exactly the definition of the columns of A being linearly independent or linearly dependent. That's exactly that definition, right? Therefore, AX equal to B has 0 or 1 solutions if and only if, right, AX, well, the columns of A, if and only if AX equal to 0 has 1 solution, 0 or 1 solutions only. If and only if AX equal to 0 has 1 solution only, if and only if the columns of A are linearly independent. Independent. So there's the theorem. So let me write it the same way I wrote this one. So defines an R by C matrix A defines a 1-to-1 linear transformation from RC to RR if and only if AX equal to B has 0 or 1 solutions only for all B in Rn, if and only if AX equal to 0 has 1 solution only, if and only if zero or 1 solutions only, if and only if the columns of A are linearly dependent, if and only if A has a pivot position in each column. So linear transformations given by matrices. When you have a pivot position in each column, the matrix transformation gives you the matrix gives you a 1-to-1 matrix transformation. When you have a pivot position in every row, the matrix gives you a transformation that is onto. And it has just, really nice properties in terms of the transformation. Right? And those properties are that you always have, 1-to-1 means you always either have no solution or a unique solution. None of this infinite solution stuff. That's 1-to-1. And onto means for every B in B, you always have a solution. You're always consistent for every B in the range. And that's if and only if A has a pivot position in every row. All right, so this pivot position business in every row or in every column, it gives you a real nice, real nice meaning in terms of linear transformations. Okay, so that's the lecture for this section.